Okay. So last time I told you that by studying the representation theory of the conformal group, we found that the generator of translations, P mu, kind of acted like a raising operator. The generator of special conformal transformations acted like a lowering operator. And we proved that there was one state in each multiplet that had the lowest possible conformal weight, right? So that state acted on by K mu would be 0. Okay. Such fields with the lowest possible scaling dimension are called primaries. The primaries are fields in a CFT with the lowest scaling dimension. Typically called delta. And each primary in the theory is labeled by this delta, its scaling dimension, and a representation of the Lorentz group. Okay. So they are labeled by delta and some representation R of the Lorentz group. So if, for example, if, let's say, phi A of X is such a primary, then its transformation properties are as follows. And remember, we justified last time only telling you about the transformation properties at the origin, and then you can always shift your operators appropriately to determine what the transformation properties at any point X in the spacetime are. So here, the action of the generator of Lorentz transformations mu and u on phi A at the origin is just sigma mu nu A B phi B at the origin. The action of the generator of dilatations D on phi A at 0 is minus I times delta phi A at 0, and the action of K mu on phi A at 0 is just K mu A B phi B of 0. And again, because this is a primary, this is equal to 0. And these generators, mu and u, d and k mu, must of course close the appropriate algebra. So the point here is that operators in a conformal field theory can be arranged into a conformal multiplet in the same way that we would arrange states in quantum mechanics into spin multiplets. Okay, we're going to touch on this again a little bit later. And the action of conformal transformations has the effect of mixing operators inside a particular spin multiplet, but never outside the spin multiplet. Okay, so operators within this grouping can shift around by the conformal transformations, but they won't shift into another multiplet. And the analogy here is with spin states in quantum mechanics, where I label the spin states by the angular momentum and the spin quantum number m. Right, so my states go L from minus L all the way through to L to all the way through to L plus L. And the action of LZ, the action of L plus and minus is to just shift between those states within that multiplet, but never outside of that multiplet. Okay. So operators in a CFT are arranged in conformal multiplets with conformal transformations mixing operators within a particular multiplet, but never with operators in another multiplet. And every conformal multiplet has a unique conformal primary. And knowing the complete list of conformal primaries allows us to know the complete list of complete set of conformal transformations. And in this way, it helps us organize the complete Fock space. Okay, so each conformal multiplet has a unique primary and once we know the complete list of primaries, then we can completely organize the Fock space of the CFT. But of course, determining the complete list of primaries for a given conformal field theory is a non-trivial task. And as I said in the last lecture, we really only know this list for a very small subset of conformal field theories, most of whom are free theories, so they don't have any interaction. Okay. And even though I said, once you know the primary operators, then you know everything you need to know about the Fock space of the theory. I haven't really told you how we do this. So the next question that you might want to address is, okay, given a particular conformal primary, how do we determine the complete conformal multiplet? Okay. So to answer this, I'm going to go back again to kind of introductory quantum mechanics and see what we did there and make an analogy. So in quantum mechanics, we learned that every spin multiplet contains a lowest spin state. Every spin multiplet contains a lowest spin state which we would call L minus L. And this state was defined by the property that if I act with the Z component of the angular momentum operator, with the angular momentum lowering operator, then that annihilates the state. So this state satisfied the property that L minus on this was 0. So this is the state with the lowest possible eigenvalue of Lz. Okay. Namely m equal to minus L. And all other states in the multiplet we can reach by acting with the raising operator, L plus. So all other states can be reached by acting with L plus. And these states are all of the following form. L minus L plus K, which I get by taking L plus and acting on that state K times. With some possible normalization, so I'll make this a proportional too. And in the spin state, we can't really apply this as many times as we want, right? Because there's only two L plus one possible states. They go from M equal to minus L to M equal to plus L. So there's a highest value that K can pick, and that's when K equal to 2L. Okay, so the largest value of K is equal to 2L, in the sense that if I act with L plus K times on L minus L, then that's equal to 0 if K is greater than 2L. Okay, and this is just a statement that there are only 2L plus 1 states in any angular momentum multiplet. This corresponds to the fact that there's 2L plus 1 possible states in any angular momentum multiplet. Like that. In a conformal field theory, the role of LZ is played by the dilatation operator, right? So it's the dilatation operator, the generator of special conformal transformations, and P mu that play the role of LZ, L minus, and L plus respectively. And a CFT, D K mu and P mu play the role of LZ, L minus, and L plus respectively. And the analog of this statement, that the action of L minus on this lowest spin state is the statement that K mu acts on the primary operator to annihilate it. K mu on some primary operator O is 0 if O is a primary. And that defines for us the primary operator, which is this operator with the lowest conformal dimension. And then we raise the dimension of the operator or the field by acting on it with P mu. Yeah, the statement is that P mu commutator with O is I times the derivative d mu on O. So what we see is every action of P mu adds a derivative to this operator. Okay, so operators that are made up of derivatives of the primaries are operators that have been raised, whose conformal dimension have been raised by the action of this raising operator. So so this operator has scaling dimension delta plus 1. And operators like this that we get by acting with P mu on primary operators are called descendant operators. So for example, the descendant operator d mu 1 through d mu n acting on the primary O has conformal dimension delta plus n if O has conformal dimension delta. So this brings out a crucial point, a crucial difference between angular momentum and conformal multiplets, namely that the angular momentum multiplet had some finite number of states in the multiplet. So if my angular momentum was L, then the most I could have was 2L plus 1 states in that multiplet, right? So if I act with L plus more than 2L times on the lowest spin state, then it's 0. Okay. On the other hand, nothing's stopping me from taking an arbitrarily large number of derivatives, right? And each derivative generates a descendant state. So I get level 1 with 1 derivative, level 2, level 3, level 4, etc. So while the angular momentum multiplet contains a total of 2L plus 1 states, each conformal multiplet contains an infinite number of states. There's no bound on how many times I can act with derivatives. Is that clear? So now we can organize the Fock space, and this is how it looks. So basically, what we have is an organization that looks like this. We organize it by irreducible representations. Irreducible representations of the Lorentz group. So let's say R1, R2, etc. Okay, so I'll have some primary O1, some primary O2, etc. Level 1 descendants will be derivatives of O1, etc. Level 2 descendants would be derivatives, second derivatives, etc. Okay. And conformal transformations mix these guys in a column, but never across the row. So now that we know how the Fock space is organized in the conformal field theory, let's see how the various fields in the theory transform. And we'll start off with primaries. So the first thing to do is to recall, the kind of starting point in this course, which was what the definition of a conformal transformation was. And a conformal transformation was a transformation that rescaled the metric. So under the conformal transformation, where x mu went to x mu tilde with some g x mu, the metric rescales from eta mu nu to, let's say, eta rho sigma dx rho by dx mu tilde dx sigma dx tilde nu, and this was some scaling factor omega to the -2 eta mu nu. This is just a statement that you make a conformal transformation, and the effect of the conformal transformation is to rescale the metric in some way. Under this transformation, a scalar primary, so this is an operator that is a scalar in space-time, will transform as follows. say omega, phi of x goes to some phi tilde of x, and phi tilde of x is just dx tilde raised to the dimension of the scalar primary delta divided by the number of space-time dimensions capital D times phi of G inverse x. This guy here is just the determinant of the Jacobian. So this is equal to the determinant of dx mu by dx tilde nu, and this is the dimension of space-time. Okay. So this is a general scalar primary. This is a scalar field in space-time. Right. We could ask more generally if our primary belongs to some general multiplet, some general representation of the Lorentz group. How does it change under conformal transformation? So more generally, if phi mu, say, or phi a, if phi a of x belongs to a general multiplet, a general representation of the Lorentz group, then phi a of x will go to phi tilde a of x, and phi tilde a of x is made up of a couple of different pieces, all of which we are familiar with already. This would just be the determinant of the Jacobian, dx by dx mu, again raised to delta over d, multiplying the spin part LAB of some R mu nu, I'll tell you what that is just now, by B of G inverse X. When this is a scalar under the Lorentz group, then this factor is just the identity, and then that reduces to what we have there. And this guy here, R mu nu, is a local Lorentz transformation. So this is equal to omega inverse dx mu tilde by dx nu is a local Lorentz transformation. And we can check this by noting that the R mu nu's satisfy R rho mu eta rho sigma R sigma nu. This is equal to omega inverse dx tilde rho by dx mu eta rho sigma omega inverse dx tilde sigma by dx nu. This factor, and this factor are precisely these factors that show up here. Actually, sorry, my tildes are mixed. All right, these three factors are precisely these factors that show up in the rescaling of the metric. And so this is just omega to the minus 2. No, it's sorry. I think my omegas were, my tildes were in the right place to start off with. That's because this then produces an omega squared times eta mu nu, which cancels out the omega to the minus 2. So this is just eta mu nu. And then this is the statement that these matrices R's act on the metric to leave it invariant, which by our definition is precisely what a Lorentz transformation does. So these are indeed local Lorentz transformations. Yeah. Okay. So now we can ask, what about infinitesimal transformations, as we normally do? If under infinitesimal transformations, omega takes the form 1 plus omega, where this is some small parameter of the transformation. And in particular, we worked out that this must be 1 over d dot psi, or lambda minus 2b dot x from our solution of the killing vector equation, conformal killing vector equation. So what that means is that this R mu nu, the local Lorentz transformations, take the following form. This is omega inverse dx mu tilde by dx nu. All right. Dx nu. I substitute in both these cases, and omega inverse is 1 minus omega. And this guy is eta mu nu plus d nu psi mu, because remember, our infinitesimal conformal transformation is 1 plus the psi, which has to be a conformal killing vector. Okay. So this is just 1, sorry, it's eta mu nu it's eta mu nu plus minus omega eta mu nu plus d nu psi mu. Okay, this is small and this is small. So this is 2 orders of small, and we drop it relative to the others. So only 3 terms contribute here. And we know that psi is a conformal killing vector, and so there's some constraints imposed from the conformal killing equation, which tells us that this guy, omega eta mu nu, must be written as the sum of d mu d nu and d nu d mu. Up to a factor of a half. And so this means that this is equal to eta mu nu minus a half d mu psi nu minus d nu psi nu, which I'm going to define to be eta mu nu plus or minus plus omega mu nu, where all of this stuff is omega mu nu. So omega mu nu here is the infinitesimal parameter of local Lorentz transformations. So omega mu nu is a half minus a half d mu psi mu minus d nu psi mu, which is broken up into two parts. We'll call little omega mu nu minus 2 b mu x mu minus b nu x mu. So these local Lorentz transformations are generated by these Lorentz transformations are generated by two things. One, these are local Lorentz transformations. And these are special conformal transformations generated by B mu or parameterized by B mu. So there are a couple of points to note. The first is for Poincare transformations. Poincare transformations satisfy the property that omega equal to capital omega is 1. For Poincare transformations, omega equals 1, and this is just the usual transformation rule. Okay. And it certainly fits with what we're finding. For dilatations, under dilatation, x mu tilde is g x mu, and this is just lambda inverse x mu, where lambda is the scaling parameter. Well, this means that G inverse X mu is just lambda X mu, which means that dx mu by dx tilde mu, yeah, is just lambda delta mu nu. So when I calculate the determinant, right, I just pick up d powers here. So I pick up. So this means that dx by dx tilde is just lambda to the d. And this lambda to the d precisely, wait, we want one above. Yeah, this lambda to the d precisely cancels off that factor of d in the denominator there. So this means that a scalar primary will satisfy that phi tilde of x is just lambda to the d, sorry, lambda to the delta phi of lambda x. So if I rescale fields, right, so if I rescale distances in my theory, right, scalar primaries, if I rescale distances in my theory by lambda, right, so multiply all the x's in space-time by lambda, then a scalar primary is a field that transforms like lambda to the delta times phi at lambda x. Okay, and it's precisely this delta that is the scaling dimension. This is why we call it the scaling dimension of the operator. So let me just end up with one last statement. Under an infinitesimal conformal transformation, where x mu goes to x mu plus some psi mu, and psi is a conformal killing vector, a primary transforms as follows. So under x mu tilde equal to x mu plus psi mu, where this guy is a conformal transformation, conformal killing vector. Phi goes to phi plus delta phi. And delta phi A of x is minus psi mu d mu phi A of x plus I over 2 omega mu nu of sigma mu nu AB phi B of x minus, I'm just going to write it up here, minus delta omega of x phi A of x. So when I said earlier that in this organizational structure that conformal transformations will mix fields in this multiplet, this is precisely what I was referring to. When I make a conformal transformation of the primary, you see by Taylor expansion that this generates this field that looks like the derivative of the primary, which is the first secondary. Okay. So this is the usual orbital part. Of the transformation. This is the spin part corresponding to the irreducible representation of the Lorentz group that this field fits in. And this part here is the spin contribution to the scaling transformation. Okay. And this is how primaries transfer. And my statement, which I will pick up again on Friday, my statement was that once I know how primaries transform, once I know this transformation rule for primaries, right, then I can work out the transformation rules for all the other fields in the multiplet. Okay, then I just need to go to a different representation, work out those, and that tells me how all of the fields transform under conformal transformations. Okay, and this is the total Fock space of the theory. All right, so it's a hell of a powerful organizational toolkit that we're developing, right? And as I said, the universality of conformal field theory is beyond string theory, right? Into condensed matter, into statistical physics, anywhere that you have these critical points in physics lends themselves to the statement that conformal field theories is a really, the mathematics underpinning conformal field theories is a really, really powerful set of tools to apply across the spectrum of physics. All right, so having done that, I'm going to stop here today, and we will pick up again on Friday when I will show you how secondary transformations, how descendant operators transform. And then I want to do a couple of examples, and I will in particular try and link up unitarity to the norm of states. I made that as a kind of throwaway comment and realized that maybe this wasn't something that you've done or thought about before. The fact that if I have a unitary theory, unitarity means something specific in linear algebra, and I was talking about the norm of the states. So I will do a toy example that is neither realistic nor particularly physical, but it will illustrate the point that I want to make, which is that if I have negative norm states in the theory, then the theory is going to be non-unitary in a particular precise sense for the Hamiltonian of the theory. And then I will show you, for example, what I meant when I said that primaries transform in a particularly nice way, but their descendants generally don't. And there, the short version of that story is that if you look at the way okay, I'll let me not get ahead of ourselves. So let me stop. Right.